So this in this session, we will be discussing about Unit 4. So in this unit, we will try and use methodologies which help us to apply graphs for various applications. Okay. So this unit will cover two important topics in graph concepts. One is minimum spanning tree and the other one is shortest path algorithm. In minimum spanning tree, there are a number of spanning tree algorithms which are available, but your syllabus covers Kruskal's algorithm, Prim's algorithm, and Solin's algorithm. The important algorithms are the basic algorithms which are used to generate your minimum spanning tree. And next one is the shortest path algorithm. So in shortest path algorithm, we are going to discuss about Dijkstra's algorithm, okay, where it is a single source shortest path algorithm. You start from one location and find out the shortest route to every other location. So that is single source shortest path algorithm. Okay, now the next one is Bellman-Ford algorithm, which is also a very similar algorithm. Okay, and the third one is Floyd-Warshall algorithm, which is a all pairs shortest path algorithm. So any node which is available in the graph can become the source node or the destination node. So you are trying to find out the shortest distance or shortest path between every two node which is available in the graph. So for which we apply our Floyd-Warshall's algorithm. Okay, now where do we apply these minimum spanning trees or where do we apply these shortest path algorithms? Say for example, I am constructing a network. Okay, I have a big company. The company is available in various locations across the world, and I am setting up a VPN, a virtual private network for my own company. And there is a network setup with a lot of switches and connections. Now, if I want to do a packet switching, if I want to do a packet transfer on my network, I have to find out what will be the shortest route or the best route for me to direct my or route my packet to the destination. Okay, so I need a minimum spanning tree, or in other words, a route which covers all the locations or all the nodes in my graph and yet gives me the minimum value. So that is called as my minimum spanning tree. Okay, a minimum spanning tree is a route which covers all the nodes of the graph, okay, wherein we say that the nodes are nothing but locations of the geographical place, okay, which covers all the nodes of the graph and still gives you the minimum cost. So that is called as the minimum spanning tree. In a minimum spanning tree, the most important condition is it will not include cycles. Okay, meaning you cannot start at one location and come back to the same location. You will pass on through all other locations which are available in the graph or all other nodes which are available in the graph. So these locations in the geographical area is what we call as the node or we call as the vertex in the graph. Okay. So what is shortest path algorithm? Say for example, you are using your food application. Say you're using Zomato or you're using Swiggy. So what happens? Uh, the customers of a particular hotel can be at any place across Chennai. Okay. Say for example, the hotel is located in Shoringnallur in Chennai. Okay, and that is a very famous hotel, so there are people who are continuously ordering food from that particular location. So from that one source, one starting location, food has to be delivered to different locations across Chennai. Now to travel from Sholingnallur to different other locations, say like Madipakam, like Monongambakam, Thorapakkam, or ECR, or all these locations, they have to find out the shortest possible route from the source to the destination. So this is possible by applying the shortest path algorithms. Okay. So with this little introduction, we will get into the topic. So in this class, we will try and cover the complete of Kruskal's algorithm. We will understand how Kruskal's algorithm works and how you can generate a minimum spanning tree from the Kruskal's algorithm. Okay. So a quick introduction. So we know what is a graph. So what is a graph? A graph is a connection of number of vertices. That connection is called as an edge and every node is called as a vertex. So vertex is represented as circles and edges are represented as lines which are connecting these two circles or these two vertices. Okay. So in this graph, in this given graph A, B, C, Okay. Uh, in this given graph ABC, A, B, and C are the vertices. Say if I am trying to represent a geographical location, now A, B, C are the names of certain places which are available. And these edges are the routes, the roads which are connecting A, B, and C. Okay. So this is how we represent a graph. Okay. So graph can be a directed graph or an undirected graph. Now, what is an undirected graph? See, we have number of examples here. So an undirected graph is a graph which has got no direction. So here from V1 to V2, you have a line, okay, which says, um, an undirected graph is a graph wherein the directions are not marked. So these are some examples of undirected graph. Now you see there are four vertices V1, V2, V3 and V4 connected by edges, okay, which are these black color lines. Okay. Now, if you want to move from V1 to V2, okay, it is possible to move from V1 to V2 also, and also reverse from V2 to V1, because there are no directions marked in these edges. So the traversing or movement from one vertex to the other vertex can be in any direction, forward direction or backward direction. So that is the meaning of an undirected graph. Now the exact opposite is for directed graph. So now you have arrow marks or directions represented. So what is the meaning of that? From 1 to 2, you can make a traverse or you can move, but the traversal back from 2 to 1 is not possible because there is no arrow mark which is representing this. So this is the difference between a directed graph and an undirected graph. Okay. So when you want to find out a minimum spanning tree, okay, so you take up these graphs and you try to find out the minimum spanning tree. Okay, so what is a minimum spanning tree? The minimum spanning tree mostly works only on an undirected graph. Okay, it works on an undirected graph. So say for example, I have to take up this first graph, this first example. Okay, this first example, and I want to find out a minimum spanning tree. So what do you mean by a minimum spanning tree? A route which covers all the nodes. So I cover V2, V1, V3 and V4. A route which covers all the nodes and gives me the minimum cost. Okay, now in this example, we will not be able to calculate a cost because the cost is not given. But generally, when we start applying our minimum spanning tree, we will have values on these edges. Now, what do you mean by these values? These values can be the amount of resource spent or time spent or cost spent in moving from one vertex to the other vertex, or to perform a job shift from one vertex to another vertex. Okay, so we will start calculating all these costs which are available. Okay, and the summation of all these costs should be minimum when you find out a minimum spanning tree. So what is the meaning of that? Do I have more than one spanning tree for a particular graph? Yes, I can have. See, the same V1, V2, V3, V4, I have tried to show you different ways of connecting them. See here, even here V1, V2, V3, V4 are connected, but in a different order. Even here it is connected, but in a different order. So all these are spanning trees except this first diagram. All the five are spanning trees for the given input. Okay, but which one should I select? That depends on the total of the cost of the edges. Okay, so every time if I have to find out a minimum spanning tree, what should I do? I have to try and find out all possible combinations of spanning trees, and then I have to find out the minimum. Or instead, I can apply my Kruskal's algorithm or Prim's algorithm or anything which will directly give me the minimum spanning tree value. Okay, so we will go back to the definition of what a minimum spanning tree is. Okay, so what is a minimum spanning tree? Given an undirected graph, okay, and it's a connected graph. Connected graph meaning every node has to be attached. You cannot have individual nodes. Okay, it has to be attached node. Okay, given a undirected graph and a connected graph, a spanning tree is the graph of the tree which spans G. Okay, meaning it includes every vertex of the given graph. Okay, and it has to give me the minimum cost value. Okay, so that it has to be a subgraph. What do you mean by subgraph? If you see this example, you have four nodes, but they are connected in the different ways. But here in the subsequent diagrams, I'm trying and selecting only few of those connections. So that is called as the subtree. Okay, so the same definition is split into simpler points here. Okay, so a spanning tree is a spanning subgraph. A spanning tree should have only n minus 1 arcs. Now what do you mean by connecting? It should have minimum only n minus 1 arcs. If I have n nodes and n arcs, then it means it can become a cycle. Okay, it can become a closed graph. Okay, it can become a closed graph. So what should I do? I should have only n minus 1 arcs. See, I have 3 nodes. Okay, so I should have only 2 edges so that they are open. All the 3 are connected, but they are open. If I add the third one also, then it becomes a cycle. What do you mean by this? This becomes a closed loop. Now if you have a closed loop, it is not called as a spanning tree. Okay, and it is acyclic, meaning it should not form a cycle. Okay, okay, so if you are able to identify such arcs, you call it as the tree arcs, and the remaining you call it as non-tree arcs. Okay, so continuation of what is minimum cost spanning tree. So what is minimum cost spanning tree? As I told you, you find out the spanning tree which has got only n minus 1 edges, but all those n minus 1 edges cost, if you add, it should give you the minimum cost. Okay, so if it gives the minimum cost, you call it as the minimum cost spanning tree. Okay, so again, another example of whatever I told you. This is an undirected graph. Okay, according to the definition, this is an undirected graph, meaning there are no arrowheads in any of the in the edges. Now, from this undirected graph, okay, which is connected, you try to create more than one spanning tree. So this is also a spanning tree. This is also a spanning tree. But which one will you select? The one which is giving you the minimum cost value. So see here I'm trying to connect these two edges. The value is 4, it is 5, it is 2. I'm talking about this cost value. Okay, so when you add these three, you get a value of 11. But if you select the other edges, if you select these edges, 4, 1, and 2, again now all the 4 nodes are connected, but the cost is only 7. So out these 2 are called spanning trees, but this last one is called as the minimum spanning tree or minimum cost spanning tree. Okay. Okay, I gave you an example of applications, but yet a quick recap of what are the applications. So when I create or when I design physical systems, interconnection of number of physical systems, I have to find out the best route covering all those physical systems. So I will use a minimum spanning tree. Okay, I told you when you send messages on a network, okay, you want to find out which will be the best path or the optimal path of message passing. So for which you need this minimum spanning tree. Okay. Cluster analysis and data storage is the widely used application right now. Okay. Now here in a cluster analysis, okay, you assume that every node that you identify in the network as one cluster. So you try to analyze which cluster should be passed through to get to the result. Okay, so that is your cluster analysis and all pairs minimum maximum path problem. Either you can find out the minimum cost path. When you can find out the minimum cost path, then definitely you can also find out the maximum cost path by just simply tweaking the algorithm. Okay, so this minimum spanning tree can also be a maximum spanning tree. But in the generic case, we never use a maximum spanning tree except for a situational requirement. Okay. So if you want, you can also find out minimum or maximum. Okay. So with this introduction about what a minimum spanning tree is, we'll start understanding our algorithms. So today in this session, we will understand our Kruskal's algorithm. Okay, now you can ask me, ma'am, why is this name Kruskal, Prim, Solin? These are the names of the scientist or the inventor who has given this algorithm. Okay, so Kruskal's algorithm was given by the person who were called Kruskal. Prims was given by a person called Prims. Solens was given by a person called Solens. Okay, actually Solens and Dijkstra together did it. Okay, okay. Now, whenever I approach any problem, Okay, I will be following a strategy, or this we call as the methodology, or this we call as the uh, solution technique. Okay, so the solution technique that we are going to apply is called as the greedy strategy. Okay, we have used this greedy strategy in number of previous algorithms, but now we are trying to understand what this greedy strategy is. So what is greedy strategy? When I have a problem in hand, okay, a complex problem in hand, my solution is not going to be acquired in a single step. Okay, I'm going to go through number of independent intermediate steps and then reach to my solution. Now at every intermediate step, okay, to proceed forward, I should have some technique to use. So that technique is called as the greedy approach. Okay, I will put it in simple terms. Okay, now what are we looking for? We will go back to this example. So what are we looking for? From this given graph, I have to find out, or I have to select some edges. Okay, now which edge will I select? Which edge will I select? I will select the edge which is having the minimum most cost. Okay, so selecting the edge is the step for my solution. Now, how I select? I use my minimum cost. Okay, so that minimum cost is my strategy here. I apply some technique, okay, here to select the edge. Okay, so this is called as the greedy strategy. So what am I greed of? I'm greed of always finding out the minimum cost. So whenever I select any edge, I'm always looking for only the minimum cost. So searching for the minimum cost is my greedy strategy. Okay, that is my greed. I don't want something which is having higher value. I want only the one which is having a minimum value. Okay, so at each stage for a best decision, you follow this greedy strategy, wanting for more strategy. Okay, to select the least cost. Okay, so in this problem we are using least cost, but some problems you can also go in for highest cost. Okay, if you are doing a max spanning algorithm, then you will go in for a highest value also. Okay, so the greedy strategy need not always be only minimum spanning, minimum value. It can be minimum or maximum. Okay, so now the first algorithm, which is called as the Kruskal's algorithm or the Kruskal's approach. Okay, so what happens in the Kruskal's algorithm? You try to build a minimum cost spanning tree from the given graph. Okay, you consider the entire graph as a collection of trees. Okay, so you call it as a forest. Okay, if you have a node, it is called as a tree. If you have a connection of nodes, it is also called as a tree. But if I have more number of nodes connected, and if I assume everything, see, if I assume this is as one tree, this as one tree, and I have connected them, then this is called as a forest. Okay, so it considers that you have a forest, and every individual node is considered as a tree. Okay, so what do you do in a Kruskal's algorithm? You select the edges to be included into the output. The output is T matrix. Okay, into the output based on the non-decreasing order of the cost. What do you mean by non-decreasing order? If we directly say, it is called as ascending order. Okay, so you arrange the cost of the nodes or costs of the edges in the ascending order and select them one after the other. Okay. Okay, you will not select an edge whenever it forms a cycle. Okay, and then you will have to have n minus 1 edges. Now, this is a condition that we got from the rules. Okay, so if it's a spanning tree, it should have only n minus 1 edges. If it has got n edges, it means it will become a cycle. Okay, so once you start seeing the algorithm, you will understand better. So we'll first work out the algorithm, and then we will try and understand the steps of the algorithm. Okay, now for an example, I have taken up this particular graph. Okay, now what I'm going to do is I am going to try. Okay, so we will take up this example. So this is my given graph. Okay, so this is my given graph. Now I have to execute my Kruskal's algorithm. So what do? I do some set of preparation as my pre-processing step. So my step one, I consider each and every vertex, okay, as an individual tree. So how many vertices I have in this graph? I have 6 vertices, sorry, 7 vertices. starting from 0. So 0, 1, 2, 3, 4, 5, 6. So I have 7 vertices. All these 7 vertices, I convert them as individual trees. So this is one tree, this is one tree, this is one tree, so on. Now, how do I represent them as an individual tree? I create sets. Okay. So what do I do? My set number 1 will have my node 0. My set 2 will have node 1. Okay. My set 3 will have node or vertex 2. So likewise, I'm going to create till S7. Okay. So what will S7 have? S7 will have my node or my vertex 6. So each one will become an individual set. So this is my first step of pre-processing. This is my first step of pre-processing. Okay, I have done this. Okay, now each one is considered as one tree with one node or one vertex. Okay, what is my step number 2? I arrange all the edges in the non-decreasing order. You saw it in the algorithm. It says non-decreasing order. Okay, so what do I do? Non-decreasing order is nothing but in ascending order. So all these edges which are connecting the vertices are arranged in the ascending order. So you start with 10. 10 is the minimum most value that you have. So you start with 10 and you finish till 28. So all the edges are given in the ascending order. So this is my preparation step number 2. Okay, so I have to do this. Then my step number 3. So whatever I told you here, see, I have represented as set of sets, and I'm also giving it as a queue. Okay, now what am I going to do is, from these values of edges, I am going to take up the first one, second one, third one in order. Okay, because I'm going to take it in order, I need a data structure to store. Okay, so I'm going to use a queue data structure. I'm going to take a queue data structure. Why am I taking a queue data structure? Because I want to use first in, first out. 10 value is the first value. I want this to be taken out first. So I'm going to use a first in, first out value. Okay, so that is why I'm using a queue. Okay, okay. Quick check. Why are we using all these data structure sets and all that? Because as a human being, I can find out the minimum cost tree by doing all this on a pen and paper. But if I have to give it to a system for an automated process, then it has to be set of data structures, set of inputs. So that is why I'm using all this. Okay, so I have created a set, I have created a queue. Okay, I am preparing my T matrix, okay, which is a 2 by 2 matrix, okay, with 0 inputs. Now what is this T matrix? Whatever I write into my T matrix is going to be my output. So I would say my T matrix is my output matrix. Okay, my T matrix is going to be my output matrix. Okay, so what am I going to do? I'm going to take up the skew values one by one in ascending order and check whether they will end up forming a cycle. When check whether they will end up forming a closed loop. If they are not going to form a closed loop, I am going to add those two vertices into my T matrix. Okay, so whatever I told you in statement, I'm going to show you now. See, listen. My value, first value is 10. First in, first out. So first value is 10. I'm going to take out the first value. First in has come out now. First out. Check whether this edge connecting 10. What are the, which is the vertices which are connecting 10? 1 and 6 are connecting this edge 10. Check whether if I add these two, will it form a cycle? No, it will not form a cycle. So add it into the T matrix. Okay, output matrix, meaning this 1 and 6 are selected for the output. This is part of the minimum spanning tree. Okay, then next, now this is removed. What is the next one? 12. 12 is the next first. So first in, first out, remove the second one. Okay, see what is 12 connecting to? 12 is connecting 3 and 4. Okay, and this is not forming a cycle. So attach 3 and 4. Okay, now quick check. I told you that 3 and 4 is not forming cycle, 1 and 6 is not forming cycle, so attach. But how will computer system know that it is not forming a cycle? Anyway, you'll have to write a program. So that is where we start using our sets. Okay, so check whether 1 and 6 are falling into two different sets. If they are falling into two different sets, then you write them into the T matrix. Okay, and then what do? You merge them. So you create the next set and you attach 1 and 6. So what happens? This will become non-existent. This will become non-existent. Similarly, 3 and 4. Okay, whether 3 is belonging to a different set and 4 is belonging to a different set. Yes, they belong to a different set. So now you create a new set which is called as S9, which includes 3, 4. Okay, what is the next value? 14 is the next value. Remove 14. Find out what is the vertices which are connecting 14. 14 is connecting 2 and 7. Is 2 available in a different set and 7 available in a different set? Yes. So add 2 and 7 and create a new set S10 which includes 2, 7. Okay, so we are going to proceed like this further. Okay, I'm going to show you step by step now. Okay, I'll repeat if you want. Okay, see, listen. I have considered the first edge 10. Okay, 0 and 5 have come from a different set, so attach it. Okay, 12, different set, attach it. 14, different sets, so attach it. 16 different sets. Why? Because 1 and 6, see, listen, 1 and 6 is in one set, 2 and 7 is in different set. So S8 and S10, they are not in the same set. So you are going to attach 1 and 2. Okay, next 3 and 6, 3 and 6. Now check 3 and 6. You have connected S8 and S10. See, now you have a new set called as S11, which includes 1, 6, 2, and 7. Now they belong to the same set. They form a cycle. So you're not going to attach it. Okay, I will show you a table here. See, listen, see this table here. Okay, so we started with 1, 6. We then went for 3, 4. Then we went for 2, 7. So what have I done? I have selected this edge. I have selected 3, 4. I have selected 2, 7. 3 are over. Okay, what is the next value in the queue? 16 is the next value in queue. What is 16 connecting? 2, 3. Okay, 16 is connecting 2, 3. Now, do they belong to a different set? Now, what are these sets? Wait, let me write it here quickly. S8, S9, S10, and S11. Okay, I'll write here S8. Okay, I'm not using the braces here. I'm just writing the values 1, 6. S9 includes 3, 4. Okay, S10 includes 2, 7. Okay, now we'll go for S11. What is S11? Which is 16. Okay, 16 includes 2, 3. Now 2 is from this set, 3 is from this set. So you merge them 2, 3, 4, and 7. You merge them. Now this S11 becomes a new set. So you add it into the T matrix. Next, what is the value? 18. What is 18 connecting? 18 is connecting 4 and 7. See, now visibly I know that it is forming a cycle. It is closing the loop. But how will I know it from the program? How will I know it in the code? See, 2, 3, 4, 7. 4 and 7 are falling into the same set. So if they are falling on the same set, I will not add it in the T matrix. Okay, I will not add it in the T matrix. I will remove it. I will ignore this value. Okay, I will ignore this value. I'll remove it. Okay, next comes 22. What are the values which are connecting 22? 4 and 5. Okay, now 4 is in a different set. 5 is in S5. So now you are creating your new set S12, which includes 2, 3, 4, 5, and 7. So this is your new set. So you include 4 and 5. Okay, next. What is the next value? 24. Find out what is 24 connecting. 24 is connecting 5 and 7. See, if I connect this, again this will become a loop. But how will I know it in the diagram? I can know it from the diagram because 5 and 7 are falling into the same set. So what should I do? I should ignore 24. Then you take 26. What is 26 connecting? 6 and 5. 26 is connecting 6 and 5. Now 6 is in S8, okay, and 5 is in S12. So I'm creating a new set which is called as S13 because they are falling in different sets, and I'm merging it. 1, 2, 3, 4, 5, 6 and 7. Okay, so you add the last edge which is 5 comma 6. Okay, so this is also considered. Okay, now the last one, 28. What is 28? 1 comma 2. Now if I put it, what happens? It becomes a closed loop. So how will I find out from the code? It is because 2 and 1 are from the same set. So I cannot add it. I have to ignore it. Okay, I have to ignore it. So now I have a minimum spanning tree. What is a minimum spanning tree? All the vertices should be connected. Now see this diagram, are all the vertices connected? Yes, 1 to 6 is connected, 6 to 5 is connected, 5 to 4 is connected, 3 is connected, 2 is connected, 7 is connected. All the vertices are connected. Are they forming a loop? Are they forming a cycle? No, they are not forming a cycle. Okay, now so two conditions are over. You have connected all the vertices, okay, and they are not forming a cycle. So what is the third condition? The selected edges should give you the minimum cost value. So how will I find out the cost value? I have to add 10 plus 26 plus 22 plus 100 plus 12 plus 16 plus 14. So this will give me a value 100. So the total cost is 100. Okay, so this is what we have tried to find out. See here, we selected 10 first, then we selected 12, then we selected 14, all individual lines. Then we selected 16, but it is not forming cycle. Then we selected 5 comma 4, and then we selected 5 comma 6. Now you have to add up all these costs together, and that cost has to be the minimum cost value. Okay, so this is your Kruskal's algorithm. So once you understand the process, we'll go through the algorithm. So this is your algorithm. You start with the output will be a null set to start with. Then for each vertex or each circle which is available in the graph, you create it as a new set. Okay, the first step that we did. Okay, the first step that we did, we converted everything as individual sets. Okay, so this is your step number 1. Then you sort the edges into the non-decreasing order. What do you mean by non-decreasing order? It is nothing but ascending order of the weight. Then you find out, when you find out that there is an edge between U and V, okay, okay, check whether they fall into different sets. Okay, check whether the set of U, say for example, you are finding out an edge called U comma V, then find out whether U and V fall from two different sets. That is why you have this non-equal to sign. If they fall from two different sets, then you merge them. Okay, then you create the union and you return back to the input. Okay, so this is your procedure. You want me to give it as your program lines, see in individual steps, then you can use this algorithm. Okay, so first it is constructing a queue where the cost is given in the ascending order. Initially we assume the cost to be 0. Then for all the nodes, okay, what do? You delete the values from the queue, find out whether the edges, the vertices connecting the edge fall from two different sets. If they fall from two different sets, you will update into the T matrix and add it in the minimum cost path. Okay, and then you perform union of the set. Okay, you will do all these 10 steps only when they don't fall into the same set. If they fall into the same set, you will just skip this if part and go finding out the next edge. Okay, so at the end of the algorithm, at the end of the while loop, what do? If you have not visited to all the nodes, then it means there is no spanning tree. Else, whatever is the cost of the minimum spanning tree, you are going to print it. Okay, so we will see one more example. This is your next example. So this is our graph. Okay, now what should I do? I have to sort all the edges. So one is the starting value, then I have two, then I have two. Okay, now question is, ma'am, when I have two edges, which one should I take? You can take any one. Okay, you can consider any one first. I can take 2 comma 8 or I can take 6 comma 5. Only condition is it should not form a cycle. Say I have 2 here, I have a 4 here, I have a 4 here. Now which one should I take first? I can take any one first, but it should not form a cycle. That is the only condition. Okay, so what happens here, you see. So for this given graph, okay, so this is our given graph. I'm going to select another color. Okay, so this is our given graph. So which is the minimum cost edge? If you go through, see what should I do? I should be creating a queue. 1, 2, 2, then 4. So likewise, I should be creating the values. I should take up all these values and put it in the ascending order. Then I should create each one as one single set. Okay, so whatever algorithm we discussed so far, I'll have to do it. Now I'm just showing you the answer steps. So see what I have done here. I have selected the minimum cost value, the edges. Okay, 6 and 7, they are not going to form a cycle, or they don't fall in the same set. Then I have considered 2 comma 8. Then I have considered uh, sorry, here 2 comma 8. Okay, so I'm connect, then I have considered 6 comma 5. Okay, I'm trying to connect them. Okay, see, I have taken this route 2 comma 8, I have taken 6 comma 5. Then what is the next value? Okay, uh, 2 comma 5. Okay, 2 comma 5 is selected. Then 6 is the minimum most value here, but if I select 8 comma 6, it will become a cycle, so I have to ignore this value. Okay, so I have to go to the next possible option. What is the next option? 7, value 7. Now if I take 8 comma 7, see, if I take this will become a cycle. So I cannot afford to give a cycle, or I cannot use a closed loop. So what should I do? I am ignoring this value also. I select this 7. Okay, then I select this 8. Okay, then if I select this 8 and then select this 8, it will become a closed loop. So I cannot use a closed loop. So what should I do? I have to remove it. This is one option. Or the second option is, I can actually remove this one and select this one. Okay, see, the values are same. Either I select 0 comma 7 or 1 comma 2 will not make any difference in the cost value. Cost, whatever cost I'm going to take up is 8, and that is what I'm going to add up in the minimum cost. Okay, so either you select this or that will be your choice. Okay, the program's choice. Okay, so in the example I have showed you by using 0 comma 7, you don't agree with me, you want to use only 1 comma 2, do it. There is no problem at all. Okay, then in the remaining 3 comma 4. Okay, now these edges 4 comma 10, 4 comma 5, 3 comma 4, and this one, all these are neglected because they are already forming a minimum spanning tree. So all the edges are connected. Sorry, all the edges are connected and they have a minimum cost value. So the total cost calculates to around 37. Now I select this 8 or this 8. This value 8 is going to remain the same. That will not make a difference. So you can select any one as you want. No conditions. Okay, no mandatory conditions. Okay, I will show you one more example. So here this is another graph. Now one important additional point that I want you to notice. See, you have a self cycle here. What do you mean by a self cycle? An edge starting from a vertex and ending into the same vertex. That is called as a self cycle. So when you have such self cycles, or whenever you have cycles, you'll have to remove the cycle before executing the algorithm. So I have removed this cycle and I have also removed this cycle. Okay, then I'm going to execute the algorithm. Okay, importantly, you'll have to remove the self cycles. Now you select all the minimum cost. See, if you visually have a glance, you will understand which is the minimum value. 2 is the minimum value, select this. This is also a minimum value, select this. 3 is the minimum value, select this. This is also a minimum value, so select this. Now problem is when I select 4, it will become a closed loop. Okay, so I should not select 4, I should not select 4. Now if I select 5, again it will become a closed loop, so I should not select 5. If I select 6, it will again become a closed loop. If I select 9, again it will become a closed loop. So I have only two options. I can either select this 7 or this 8. I will take the minimum value, so I'll take 7. So this is my minimum spanning tree, minimum cost spanning tree. Okay, one more example. This is another example. Okay, so see here, you have taken all minimum cost values and you've added them together. Okay, we have not considered this 12 because it will form a loop here. See, this is a closed loop. So I don't want closed loops to happen. Okay, I don't want closed loops to happen. So what should I do? I'm removing this one. Okay, similarly I'm removing this one also. Whichever is leading me to form a closed loop cycle, I'll have to discard those edges. Okay, and this is my last example. Okay, see, this is forming closed loop, so I am removing. This is causing closed loop, so I am removing. This is also causing closed loop, so I am removing. The remaining things become a part of the minimum spanning tree. Okay, so in this session, we understood what is a minimum spanning tree. We understood what are the applications of a minimum spanning tree. Okay, and then the various algorithms, just the names. We understood that there are two more algorithms to discuss, Prim's algorithm and Sonnen's algorithm. In this session, we detailedly understood the Kruskal's algorithm. So next class, we will go in for Prim's and Solon's. Okay, thank you.